tonight. We're going to go through several stories about how we can determine the origin of things that are on this planet Earth. We can provide, as scientists, the tools to unlock just what has happened to many of the everyday objects around us. Our phones, appliances, our clothes, your artifacts that you love in your house. And we can tell where they came from, where they are now, through the application of a range of investigative tools, including geoscience, where we are celebrating here today in Edinburgh the history of science at the Edinburgh Science Festival 2026. Scientists combine many different disciplines, chemistry, biology, geology, geography, and data science, to help understand and evidentially establish authentication, provenance, traceability, and origin. And that helps us to find missing people and objects. Soils and minerals are like fingerprints that can link objects with places, with methods becoming more and more sophisticated that we can use, linking to the location anywhere in the world, georeferencing location. Geoscience covers and delivers widely to the United Nations Sustainable Development Goals, reducing poverty, producing safe quality food and ensuring that we have healthy air to breathe, water to drink, and safe land to grow crops on, educating and mentoring our next generations, improving equity and fairness across the world, understanding and improving energy creation and its safe use, helping the economy in a safe and productive way, enhancing sustainability, understanding markets and geopolitical issues, very, very important, particularly at the current time, and enhancing climate resilience strategies. And through data and evidence, helping bring about peace, justice, and strong, sustainable institutions. And we do this by working together through partnerships, such as with the Edinburgh Science Festival, James Hutton Institute, the Scottish Government Research Institutes, the International Union of Geological Sciences, SASA, the Brazilian Federal Police, and media organizations such as Reuters. We will tonight be looking at the science of origin as applied to elements and minerals essential to our everyday lives. They all originate from the earth beneath our feet. Precious metals, precious artifacts, and human beings. Mineral resources are essential to modern society and future green technologies, supporting sectors, from energy to healthcare. However, their high value fuels organized crime in illegal mining, where forensic geology plays a vital role in assisting law enforcement and preventing environmental harm. The science of origin also helps fight wildlife crime and locate illegal burial sites, using similar approaches and techniques, applying the same core principles, correct sampling techniques, high degree of rigor, evidence, chain of custody, integrity of samples, and of course the collaboration and inspiring the next generation of scientists, such as some of you here tonight, and to develop new methods to bring justice and peace in our world. The use of satellite and remote sensing technologies going from large scale to the detailed scale understanding, revealing not only what's on the ground, but what lies beneath the earth. This is where the science of origin moves beyond materials into human history. By detecting what lies beneath the ground, we can uncover hidden crimes, illegal burials, mass graves, and sites of atrocity that were deliberately concealed. The power of these methods lies in their objectivity. The soil, the sediments, and the geophysical signatures hold an independent record of what has happened to that material. That evidence supports justice, accountability, and reconciliation, and demonstrates just how geoscience contributes directly to peace, justice, and strong institutions. So tonight, we are delighted to welcome 4 international experts on our panel. These guests have worked on practically every continent on the planet. They are experienced in a wide array of the application of science to the question of origin and establishing evidence that can do so. So thanks again to the James Hutton Institute for hosting this event alongside the International Union of Geological Sciences initiative on forensic geology, allowing us all to be here with you tonight. Our funder and chair, Lawrence Donnelly, is here, and he's going to talk about search strategies in metals and minerals. Fabio De Silva, is going to be talking about the precious gold and how can they provenance and trace those gold substances. And in addition, we welcome Lucy Webster from SASA, the Science and Advice for Scottish Agriculture, who will be covering the important topic of wildlife crime. And Ryan McNeill will discuss the use of geosciences and data science in uncovering atrocities across the world. Thank you all in the audience for coming here tonight. We are certainly now going to go global with a geo twist. So welcome to our panel. So first up tonight is Ryan McNeill. Ryan is the London-based enterprise editor for geospatial investigations at Reuters and specializes in remote sensing and large-scale data analysis. Ryan.
Thank you very much. It's an honor to be with this group. I'm not a scientist. When you're growing up in the US, we watch Sesame Street, and there's a little song about one of these things is not like the other, and that's kind of the situation. But I am a journalist, and an investigative journalist, and we rely on science, and I'm going to show a little bit about that. More specifically, I'm a data journalist. What does that mean? It means that it's a journalist that has one leg in traditional journalism and another in data science. And generally, I specialize in analysis of geographic data, including data generated by satellites. I love geographic analysis because it gives us precision. If we know the where, we can investigate the why and the who is responsible. And when I speak to other journalists, I have this rant about how important it is that we understand that satellites aren't just pretty pictures. In journalism, an awful lot of the work, sort of like OSINT work, focuses on visual review of RGB imagery. But satellites have sensors that are collecting data that we can leverage to extract important information. Think of it like a spreadsheet. Each record is a pixel, a place on Earth. And each column are values from, say, the visible and invisible light spectrum. Red, green, blue, shortwave infrared, so on. And so we can manipulate that data to track things like vegetation health or fires. For example, the classic method of analyzing vegetation health is simply a ratio of near-infrared and red divided by near-infrared and red. These types of formulas, there's entire textbooks on this stuff, can help us identify the signs of war and conflict, destroyed buildings, burned crops, and so on. And so originally I was interested in satellite data for environmental investigations, but somehow I stumbled into using those skills to help cover conflict and atrocities. And since the Sudanese civil war broke out in 2023, it's become my main focus, which perhaps unfortunately is a sign of the times. After Syrian dictator Bashar al-Assad fled Syria, Reuters dedicated a lot of resources to covering the new Syria. We were, of course, investigating the crimes of the old Syria under Assad, but also the new Syria. We sent reporters into Damascus. They went to security ministries and photographed thousands of documents We built sprawling infrastructure using AI tools to extract handwritten Arabic writing and make those documents searchable. More on that in a minute. And we followed tips. One tip was about a mass grave in the Dumer Desert. We didn't know where it was located or how big. A colleague met a mechanic at a shop in this little town of Dumer, and you can see it there, who had worked on the trucks used to carry the bodies. Now I'm going to pause a moment and I'm going to go ahead and give away the story because it's important for the rest of this. It's a dark one. Thousands, likely in the tens of thousands, of Assad's victims had been buried in a mass grave near the town of Katafa. The site had been exposed, including by the New York Times and other news organizations. And when Assad thought he had won the civil war, his allies, the Russians and others, told him they were working to reintroduce him to the world, but first he needed to clean up all these atrocities, the chemical weapons, the mass graves, and the bodies at Katafa. And remember those documents we collected? They helped us figure out that Assad had turned to a certain colonel, known as Assad's master of cleansing, to clean up Katafa. So through our reporting, we were able to place this conspiracy inside the presidential palace. And the master of cleansing began an operation, which was known as Operation Move Earth, that consisted of digging up every grave at Katafa. They placed the bodies into trucks, not with any care, but with mechanized equipment, by the load. For about 2 years, 8 trucks each night carried bodies from one grave to another. The only thing that stopped work was COVID. As the truck carried bodies along the highway, they left a trail of stench that people remembered even to when we came a few years later. When my colleague visited this mechanic's shop, she found a mechanic who'd been holding a deadly secret he thought he'd take to his grave, lest he end up buried in one of Assad's graves himself. You know what? As journalists, we couldn't do our jobs without brave people, brave everyday people like this mechanic who are willing to talk to us. And turns out trucks would stop at his shop for work. But one night, a truck broke down at the new mass grave. The mechanic remembered the location, and he took us there. And this is it on the screen. And this really, to me, conveys the size. You can see the people there, and the trenches go all the way back to the base of those mountains in the background. But yet, from the ground, it's hard to tell exactly what you're seeing, right? But this animation, which was actually the first thing that I looked at, very kind of medium resolution with near-infrared band, and you can see occasionally the construction of gigantic trenches. And like I said, this is relatively medium resolution imagery. And I've worked on mass graves enough to say I've never seen anything like this in this relatively lowish resolution imagery. My first expression was, oh my God. We knew this was different. That little GIF a minute ago immediately told me Dumer was not like the other mass graves we had investigated in Syria. If these trenches showed up on medium resolution imagery, imagine what the very high resolution imagery would reveal. So fast forward into our reporting. This kind of public service journalism takes a long time, and I'm thankful to work for a news organization that's really willing to give us the time to do it and the money to do it, and the people to do it. I had spent months using multispectral analysis using mapping software to document the excavation of graves at the original site and the filling of new graves at the new site. We wanted to show quantitatively that work at these two sites had occurred in tandem. We identified 34 trenches, 2 kilometers of trenches in all. During one call, my colleague made the comment that one of her sources had noted the color of the soil in the truck. And as an example of how journalists can sometimes miss the forest for the trees, I was so singularly focused on documenting these trenches that I hadn't paid attention to the rainbow of colors we were seeing in the satellite imagery that you see here. And I thought, I bet there's a scientist who might know a thing or two about this. Think of investigations like a prosecution. While we had already built quite a bit of evidence, every layer matters. And if we could show through some sort of methodology that perhaps this soil came from somewhere else, that would be sort of the cherry on top to our body of evidence. So thank goodness Lorna found time in her busy schedule for us, and she assembled 2 other experts including one who specializes in using drones to investigate graves. We learned it's tough to investigate soil colors using satellite imagery because of atmospheric interference, haze, clouds, whatever. But drones are not affected by those issues. We had a drone in Syria, and the drone expert coached our drone pilot on how to fly it to create a scientific scan, as opposed to the typical kind of oblique angles that we do for photojournalism, right? And Katefa, this is the original site, turns out had 3 pits that geologists were able to use as visual references to compare the subsoil color with Duber. Now, those trenches or those holes, we don't know why they were dug, but a very good possibility is it was loved ones looking for family members and friends, which typically happens in mass grave situations like this, and they found nothing there. And so at our second site, we built these, the white are the control samples, and the red is the disturbed earth where the trenches are located. And we found, thanks to the help of our scientists, a distinct color shift. And to measure these shifts, we used, quantitatively, we used the Munsell system, a 3-dimensional system to measure soil colors. The disturbed earth, and this is an example of one sort of area, according to the Munsell analysis, became redder and darker. Now, how does that happen? Those subsoils, the scientists determined that that kind of shift would occur with the addition of just the kind of yellow and red subsoils that we could see just beneath the surface in that original site. And we ended up learning that we had human reporting, we had satellite imagery, and now we had forensic soil science that helped point us toward one thing, which was Dumer was a mass grave, and it was filled with bodies exhumed from Katefa. And none of these would have been okay on their own, but together, they were very powerful. And this story, I think, also demonstrates the power of what happens when journalists and scientists collaborate. So what's the end result? And then I'll be quiet. Near the end of the year, Syria's new government announced that it had assigned soldiers to guard this site, which was unguarded every time we visited, and announced that they were beginning a criminal investigation. They were beginning to map the site, and were working with international organizations to begin what no doubt will be an enormous task to try and document the bodies that are buried there. Thank you.
Thanks, Ryan. That was wonderful. Thank you very much, Ryan. What's your thoughts on how the work that we did in Syria could be useful in other situations?
Well, a lot of our work, including Darfur and other places, the world is getting more dangerous for journalists to do their work. There are many places we can't go. So if somehow we can extend this science to other places that we cannot visit, I think that's potentially very powerful.
Absolutely. Thank you very much. So we'll move on. We will have time at the end where we have a large question and answer session. So you will get your chance to ask your questions. So keep them there in your mind. Next up, we have Dr. Lawrence Donnelly, who is a chartered geologist, and he is chair of the International Union of Geological Sciences Initiative on Forensic Geologists. Lawrence.
Thank you, Lorna. Ladies and gentlemen, good evening. It's my absolute pleasure to be here tonight to talk to you about forensic geology. I've spent most of the past 35 years working with police and law enforcement in many countries around the world, mainly in geological trace evidence, examining crime scenes, and searching the ground for burials related to homicide, serious organised crime, and counter-terrorism. But tonight I'm not going to talk about that. I'm going to talk about the illegal mining and the illicit trading in minerals around the world. If it can't be grown, it has to be mined. What do I mean by this? Every item in your life comes from the ground. Just think of your mobile phone. It contains 25 or more metals. The flat screen touchscreen contains rare earth minerals. There's gold coating the wires. The battery contains cobalt, lithium, copper, aluminium. Your phone vibrates because of tin, tungsten, tantalum. Think of the number of metals and minerals in your vehicle. These have to be mined. So-called green energy from solar panels contains germanium. The average electric car contains 4 times more copper than a petrol car. Mining and minerals have underpinned civilization since the Stone Age, when we used flint as tools. The Iron Age, the Bronze Age, the Industrial Revolution, the Digital Revolution, the so-called Battery Revolution, all require minerals. Mining and minerals have generated billions of dollars. Entire cities have grown up because of mining and minerals. But where there's money to be made, there's crimes to be committed. A quick search of the internet will give you a feel for the increasing crimes that are taking place in the minerals and mining sector. But we also have evidence. We know, for example, from our work with the FBI, with Interpol, with federal police agencies, that 80% of gold coming out of Colombia is illegal. We can see from the graph on the bottom left, the number of seizures of gold from the Brazilian federal police is increasing year on year. And my colleague and friend Fabio will speak more about that shortly. We know that many of the cartels in Mexico and Colombia are no longer trafficking cocaine and drugs, but minerals. They're easier to transport. They make more money. This is underpinned by sophisticated digital banking and international money laundering schemes. The Sahel region of North Africa, shown in orange, is occupied by the Wagner Group from Russia. They control most of the gold that is smuggled through the Mediterranean to India, the United Arab Emirates, and Turkey, before working its way into Russia, funding the war in the Ukraine. In addition to Russian gold, there's the Taliban. Afghanistan is an immensely rich country. I've been fortunate to work on the Afghanistan-Pakistan border. So many minerals there. Just take a look at the list in the middle to give you a feel for the mineral wealth of Afghanistan. These minerals are working their way into global supply chains, are becoming legitimized. We know that transnational organized crime groups are also smuggling diamonds, gemstones, rubies, and emeralds to raise finance for international terrorist atrocities. Terrorists require financial resources. How do they get that? One way is by trading minerals. I was asked a question about 4 or 5 years ago by a Brazilian federal police agent. He said, Lawrence, tell me, you're a geologist, you're a forensic geologist, what mineral or metal makes the most money for drug cartels and terrorists around the world? Good question. I didn't know the answer. Gold, platinum, palladium, diamonds? I was wrong. It is sand. Illegal sand makes $350 billion a year for cartels, exceeded only by the drug trafficking and trade in pirated and counterfeit goods. Why sand? It's required in the civil engineering industry. Illegal sand mining exceeds the value of illegal gold, diamonds, and precious stones combined, which is about 48 billion. Illegal mining is essential for the cartels. But what can we do as geologists? Well, there's 2 things we can do. The first question a police officer may ask us is, where is it from? From where is this sample? In other words, is there a link between the sample and the offender? Well, we can do this because of a fundamental principle of forensic science called the low card exchange principle. And what this says is when 2 objects come in contact, there's always a transfer of material from one object to the other. That transfer might be short-lived or beyond detection, but it's taken place. So a criminal may break into this building or your house and wear gloves to not leave behind fingerprints or to protect him or herself in terms of leaving DNA. But they will not know, they may not know, that if they introduce soil into a location or take soil away, it's transferable. This is our DNA effectively. If you look at these rocks at the bottom, basalt, sandstone, dolerite, they have particular names because of the mineralogy and textures. Look at the everyday products above, cement, glass, solvents, pesticides. They have unique textures, so we can trace them through supply chains. But not just minerals, also pollen and microfossils. The sand grains on the bottom left, if you commit a crime and wash your clothes, then potentially we can take the residue, the lint from your dryer, washer, look at the quartz grains and place you at a crime scene. So if you do commit a crime, burn them, don't wash them. But even if you burn them, it's highly unlikely the fire will be hot enough to melt the silica grains. So beware. The second question a police officer may ask is not what is in it, but where is it from? And in the United Kingdom and other parts of the world, we can answer this question because we have geological data. The map on the left is the United Kingdom with all the towns and buildings stripped off. Those of you not familiar, the rocks tend to get older from the southeast, where they're a couple of million years old, to the northwest of Scotland, where they are a few hundreds of million years old. They're covered in soils, shown on the right, organic materials, silt, sand, etc. And we have excellent geochemical data. I'm showing here the nickel data for Cornwall. So wherever you go in the country and the world, you take with you sediments and sand. So if I examine your shoe or your clothes, even on a dry day like today, you've likely picked up trace evidence. We can probably identify how you got from your house to this building. So geological materials are effectively useful for law enforcement. Quick example, this is a town in the Peruvian Andes. It's not a pleasant place to live. You've got human rights violations. They mine gold. Swiss refineries do not want to buy gold from this town to support crimes. So by using isotopes, which will be explained later by Lucy, and by understanding the mineralogy, we can avoid buying these materials. The two gold examples on the left, this is a gold bar, which is not a gold bar, it's gold leaf covering copper, and the drill holes identify that. The gold in the middle has a tungsten core. Tungsten has a similar density to gold, and this was legally traded on the New York and London stock exchanges. And the image on the right shows how we can see the contamination of copper with iron. This material is worth about $25 million. After our investigation, we was able to prove to the mining company that it was adulterated. A few examples: Operation Greed by the Brazilian Federal Police a couple of years ago led to 82 people being arrested, 280 million in seized assets, $3 billion in halted transactions on stock exchanges and global banking. The example on the right with Interpol, seizure of cyanide, active charcoal, etc. So working with law enforcement and geologists can really be quite powerful in detecting, deterring, and disrupting operations. It's not just about metals and minerals, illegal fossils. There are hundreds of millions of dollars worth of fossils traded each year. They're a status symbol. Some dinosaurs are traded for up to $10, $20, $30 million. There's also fake dinosaurs coming from China and other parts of Asia. But not just dinosaurs, diamonds. I'm a trained geologist, but I'd struggle to tell a fake diamond from a real diamond unless I've got instrumentation, emeralds and other gemstones as well. In 2002, I went down to Westminster Palace to talk about forensic geology. This developed an interest in forensic geology and led to the establishment of the International Union of Forensic Geology. International Union of Geological Sciences Initiative on Forensic Geology. We work with police and law enforcement, scientists and geologists around the world to develop and promote forensic geology globally. There are now many books, papers, and documents on forensic geology. Many of them are free, so if you're interested, make contact and we can send these to you. So in summary, I hope I've been able to demonstrate that forensic geology can aid and assist police and law enforcement. We can examine and investigate crime scenes. We can provide geological trace evidence to eliminate or implicate a suspect that might be presented in a court of law. We can search the ground for burials, and my colleague, previous presentation, demonstrated that incredibly well. And we can investigate mining crime and the illicit trafficking of minerals around the world. And finally, why do geologists work with police and law enforcement? Because it's the right thing to do. Usually there's a mother, a father, a family who's negatively impacted by a crime, and hopefully our contributions can bring some closure and some justice. Thank you very much for your time.
Thank you, Lawrence. So you'll all be checking your washing machines tonight when you go home. Thank you, Lawrence. Just a quick question. What are the main ways, do you think, science, and particularly forensic geology, can assist the police in detection, disrupt, and displacing crimes associated with illegal mining you've been telling us about?
Thank you. Police and geologists have a number of things in common. We're both interested in the ground. We call it exploration, the police call it search. We're interested in soils and minerals, usually to find resources. The police were interested to catch a criminal. We often have impartial data and information. We have this much time to make a decision that has that much impact. The police are the same. So what we can do is we can use our techniques and methods, and we can adapt them and adopt them in a law enforcement context. And we find this works incredibly well. So even though our backgrounds are totally different, our objectives are very similar. And over the past 30 years, that's proven to be quite successful.
Brilliant. Thank you, Lawrence. And next, we have Fabio da Silva Salvador from the Brazilian Federal Police. And Fabio is going to be telling us about the secrets of gold.
Okay.
Thank you.
Good evening, everyone. I'm honored to be here in Edinburgh, land of great geologists and great scientists. Yeah, I'm a geologist. I'm a forensic geologist in Brazil, in Brazilian Federal Police. And for me, it's very easy to explain my presentation after the presentation of Lawrence. I will present to you a specific case and a specific necessity of Brazilian Federal Police and Latin American police are the traceability of gold. Gold is a great richness, but maybe a great problem, a global problem. In Brazilian Federal Police, continually, we have different seizures of gold in different forms, in different aspects. And the question in Brazilian Federal Police is, exists one natural signature in gold with the capability of trace the gold from the origin at the manufactured materials of gold. All of us using cell phones, as Lawrence speak, and all of us using jewelry. But the gold of this jewelry, of these cell phones, our knowledge, where come from this gold? This is different types of seizures of gold in Brazilian Federal Police. Jewelry, bars, gold bars, jewelry. And the question is, it's possible to define an unique signature of gold from the ore to the end of the chain of transformation of gold. The signature of this gold is preserved in different steps of transformation? If yes, we have a solution by transnational crimes and great social and environmental problems around the world. At this moment, in Brazilian Federal Police, we use different tools to try to define this provenance of gold. If this gold is extracted in legal mines, illegal mines, or indigenous lands, where comes from this gold? If we define the signature, the signal of this gold, and this signal is preserved in all the chain, the problem is solved. But it's not easy. In this moment, we use two different tools for this objective. We use the geochemistry of gold and the isotopy of gold, in gold. Because gold have in your composition different elements, trace elements. These trace elements for geochemistry is not possible to use to define the provenance. But the use of isotopy is the best tool at the moment. Main, the lead isotope. The lead have 4 different isotopes. And the combination of these isotopes in gold expose the provenance of this gold associated with the geological deposit. The proportions of these 4 types of isotope of lead is the more advanced tool, the most advanced tool to define the provenance of gold. But it's not easy because this is traces of lead inside the gold. But in refined bullion, in jewelry, and in electronic components, it's totally possible to find the relationship between different isotope relations. And this is the state of art of traceability of gold. It's not a state of art because state of art are continuously up ground, you know. In this moment, we have studies at nanoscale. In nanoscale to define the atomic properties of gold. If these properties are useful to define the provenance of the gold, it's a tool for Brazilian Federal Police and polices around the world, okay? This is a case study of a little pepita, nugget, okay. A gold nugget found in Brazil with no provenance, indefinite provenance. Where this gold nugget come from? We use different methods, geochemistry, isotopy, and nanotechnology, and define nothing. It's nothing possible to define where comes from this nugget. But we advanced in the studies. Well, this is the content of my presentation, the use of modern technologies, modern tools to define if the gold in this room have a provenance knowledge, okay? And it's very important, and this meeting is very important for me, to explain about the importance of new generations of students, of science students. And for this, here we have some points in Brazil and in Latin America where the students are involved in try to develop new methods of traceability. It's basic. As Lawrence explained, the continuous development of new generations is fundamental, is important for the development of science around the world. So Brazil have 14 groups of young students. In this moment, research the provenance of gold with me, and another countries in Brazil, in Latin America, sorry, and another countries. Well, this is a group, a network, a net of scientists around the world study this problem of interesting for all the society, all the global society, where come from the gold circulating around the world. Okay? Thank you so much. Thank you.
So Fabio, in your area of expertise, why do you think gold is so widely discussed as the store value? Do you think it's solely the economic value of gold?
Gold have ancient value. And if we find the provenance of gold, a great number of problems around the world was extinct. But it's a utopia, because the rich countries and the poor countries have different ideas about these transactions of gold around the world. The Latin America and Africa are producers, and another countries, rich countries, are consumers. Okay?
It's not fair.
Not
It's not fair. Next, I think we'll have more, hopefully we can rush on, and next is Dr. Lucy Webster from SASA in Edinburgh. Lucy.
Thanks very much, Lorna. And tonight I'm going to be talking about the illegal wildlife trade, which I've just found out just misses out on the spot where the illegal trade in sand hits in transnational organised crime. But it is a crime that is estimated to be worth around £15 million annually. And the iconic species, your tigers, your rhinos, your elephants, get a lot of press, but actually they're just the tip of the iceberg. So we're also talking about pangolins, about tropical timbers, insects, fisheries, other marine products, or even closer to home, the illegal theft of wild peregrine falcons down in the borders. We have a lot of legislation in place to allow legal, sustainable trade in some of these species. However, where the demand is really high and there's profit to be made, obviously there's the temptation to trade illegally. And unfortunately, the scale of illegal trade absolutely dwarfs the legal, sustainable trade in these species. So the nature of wildlife crime is they tends to happen out in the wilds. And for example, illegal logging is thought to happen at a rate of around 1 football pitch size of deforestation every 2 seconds. So by the time I finish talking this evening, around 250 football pitches of forest will have been felled. decimating habitats for thousands of animal and plant species. But although people don't see these crimes where they happen, where people can potentially be caught is at the border, at the transactional point between countries. So we're at the border. We've opened up some stuff. It looks a bit different. What do we do now? How do we know if it's legal or illegal? So the most common questions are, what species is it? Is it legally protected? And then also where it's from. So this schematic sort of gives you the idea in the top of the sort of different evidence types, different bits of animals and plants that we might find in trade. And then underneath is the evidence that we can glean from those items in trade. So the biological evidence, the DNA, the protein, or the chemical evidence, chemical signatures specific to that species or that location, or indeed the soil evidence that may be transported with items in trade. So if we move back to our first question then, what species is it? Well, with over 38,000 species protected in trade, even if you could identify them all by eye, and I dare any of you to say that you can, actually, normally, they're sort of processed, so they're sort of chopped up into pieces or heavily processed, so you can't really identify them morphologically by eye. So we can use DNA, so we can compare DNA sequence with the seized item in trade to a reference database and see if we can identify the species of origin. But unfortunately, DNA is not always easy to extract from all items. And here I'm talking about timber, really. And this is where chemical signatures can come into their own. So there can be unique chemical signatures for specific species. And again, you compare with a reference database from what you've found in this sawn timber in trade, you can establish the species that it comes from. So once you know what species it is, the next question is it protected? So we have the Convention on International Trade in Endangered Species of Flora and Fauna, or CITES, and over 180 countries around the world have signed up to this convention. It is a trade convention, but in order to be under the umbrella of legal trade, the specimen would need to have been collected legally within the country of origin, with a note on sustainability, but also to be traceable through documents like permits. So if at the border we've identified that the species is listed on CITES, but there were no permits associated with it, then we obviously have illegal trade on our hands. So the next questions then come on to where is it from? And initially I'm going to talk about whether it's from captivity or whether it's from the wild. So due to the demand in wildlife products, producers have established legal captive breeding programs or indeed growing plants in captivity, farming, I should say. And in order to identify if a specimen is from one of these farms, you can use different types of analysis. And the example I'm going to give is I'm going to go back to those peregrines in the borders. So within the UK, we actually have a very flourishing falconry trade where people legitimately breed falcons in captivity, and then they obtain permits in order to export them from the UK. In those permit applications, they have to declare the parents of the offspring. And what we can do is use DNA profiling, that's what the image in the center is, to compare the profiles from the declared parents and the offspring to see if that family tree actually works out or if the offspring might actually come from a wild nest. Another side to the where is it from question is where is it from geographically? And now I'm going to be talking about elephant ivory. So the image on the left is a seizure of elephant ivory in Singapore. And DNA analysis can tell us a lot about where that ivory might come from. But where it comes into its own is when it's combined with chemical analysis as well. So thanks to Lawrence for asking the DNA scientist to explain stable isotopes. But the image on the right is an isoscape. So this is where all of the individual dots are locations where the ivory has been sampled. It has then been profiled, in this case, for this particular map, for the isotopes of sulfur. And the different colors tell you how much of the heavier isotope of sulfur has been found in those samples. So you can see here we've got a very strong signal. In the south of the country, it's very red, showing quite a lot of the heavier sulfur isotope. And in the north, it's more green, so there's less of that isotope. If we're only looking at one isotope, we can't really tell very much. So an item recovered in trade, we might be able to say if it's from the south or from the north. But what you can do is you can overlay results from multiple different elements to get a really fine scale resolution. And when you combine that with DNA analysis, you can actually get a very fine resolution on where the ivory is from. In addition to what the actual item in trade can be used, wildlife products are often transported with soil. So soil, as we've already heard, can be very invaluable for geolocation, and plants grown in captivity will have a very different soil composition from their wild counterparts. Animals tend not to have soil on them, but animal parts can sometimes have soil associated with them if they are perhaps buried to hide them before they are exported from a country. So soil can also play its part in identifying illegal wildlife trade. So tonight I've talked about the biological and chemical side of forensic science and what we can do with the illegal wildlife trade. We can provide evidence that not only identifies the species of origin, but also potentially where specimens have come from. When we know where things have come from, the police can then identify trade routes, which really allows them to then start to look at places in detail to identify the organized criminal networks who are responsible for decimating our biodiversity worldwide. Thank you very much.
Thank you very much, Lucy. That was absolutely brilliant. So following on from that, the use of biology, chemistry, isotope chemistry there, what do you think is the biggest barrier to these being used routinely in wildlife investigations?
Okay, so there's a couple of barriers. One of them is really money. So wildlife crime doesn't always top the bill when it comes to priorities, but also there's not always the available data sets. So all of those comparisons that we're talking about, particularly for geolocation, you don't always have a complete picture in the data set that you have. And then if you can't actually answer somebody's question, they get a bit bored with asking you, oh, can you tell me where this has come from? Oh, no, I don't have a data set for that. So it's sort of having the resources. So we're building the picture. It is happening, and we're working internationally with partners to try and build a better picture so that we do have the resources to say where things have come from, but we can't always do that at the moment.
Well, hope it gets better. We have got about 5 minutes, 6 minutes left. So we've got the magic throwing. Yep. Has everyone got? We'll have time for one question to each of our panel. So who's got a question for Ryan first? Question for Ryan? Yes, we've got one there. Say your name and then the question out loud, please.
And my question to you is, with the quality of satellite information that's available, if more of that was available to journalists, would you know a lot more about what is going on in the world right now? So that what you presented was very powerful. I didn't know it, but very retrospective. But actually, there must be things going on right now that we know about, or governments know about, and is that information there and available? And what makes it available to the wider public?
Well, if I understand your question, I think you're really touching on the third rail right here, because we're learning right now, the Trump administration has put pressure on US-based commercial satellite companies, and the flow of data in not just Iran, but across the whole theater has been, first, it was subject to I believe it was a 96-hour delay, then it became a 14-day delay, and now it's not at all. So we are very, when it comes to very high resolution imagery. We're learning really fast that we cannot rely solely on American-based companies, at least in the current climate, and we need to diversify our sources of data to other countries. We're seeing now, Airbus, they're European, obviously, and we're still able to get some data through there. But yes, always, yes, more data would allow us to tell more stories and to investigate more things. And this is sort of, we're facing this unprecedented blockage of data. And I don't know where this leads, but it's clear that we're going to have to think about this in the future. Because it's so critical for how we tell stories about, and then I'll shut up, when we covered the Sudanese civil war, my colleague went to the IDP camps on the Chad border, and these are people who have been through tremendous trauma. Women who've been raped or had their kids just killed, and they miss, maybe they get a date wrong, or we know that trauma obviously affects people's, so satellite imagery can be really key in triangulating those stories. And I can tell you numerous cases where we had to go back to sources and say, are you sure you were here? Are you sure? Because we couldn't verify it with satellite imagery, and it made our story and our journalism more accurate. You've really touched the third rail. Yeah.
Thank you, David. Thank you, Ryan. Question for Lawrence from the floor, please. Yes, we've got one here. Sharon. Yeah.
Hi there, Sharon Simpson. Do you have a particular case that you're particularly proud of, where the geological work has clinched it, has provided evidence that has made a huge impact as to the final outcome?
I think the examples I showed in Brazil, where geologists were working with the federal police, and the deployment of an operations team who can abseil out of the helicopters, destroy the mining equipment with a very special explosive that doesn't damage the jungle, seize the gold, prevent $300 billion of international transactions, seize $318 million in gold, arrest 82 people, seize 600 vehicles, so on and so forth. That's just one operation. And this is happening regularly. So that one in particular, I think globally stands out. Thank you.
Thank you, Lawrence. And a question for Fabio from Brazil. We've got a lady there.
Incoming.
So is this working? Yeah. If I was gonna trade legally mined gold, what I would try to do is probably melt it down with legitimate gold to dilute the isotope of the illegal gold. Is that a scenario you encounter, and does it cause any problems to your investigations?
Good question, if I understand. The big problem is the moisture of different origins of gold. If I have one provenance, and expected provenance, and one material, the comparison is very easy. But if we have different moistures of gold in the origin, or in the next steps of the transformation of gold, the difficulty is very, very incremental. But it's possible. It's a mission of the science. It's not impossible for the science, as we have equipments, we have knowledge, but the support of these investigations are prioritary, and it's not too easy. Okay.
Thank you, Fabio. And one last question for Lucy. Yes, we've got someone keen up there. Thank you.
Thank you. I'm thinking about wildlife crime being the illegal
exploitation of species, but obviously there's also quite a lot of legal exploitation of species and natural resources. I'm just wondering if there are opportunities or whether there are instances of links between the two and the science behind the traceability of the products from wildlife crime. Can that also help inform consumers about the provenance of things that they're buying, where it doesn't come from illegal exploitation, but it comes from still legal?
Yeah, yeah. So that's where your certification schemes come in. So for example, in the UK, we have the Marine Stewardship Council. So when you're buying your fish from the supermarket, look for a MSC certified fish, and they have largely documented traceability chains, but they do also verify their chains with some DNA testing as well. Likewise with the Forest Stewardship Council as well. These certification schemes really help consumers to be able to buy things from sources that are well managed and are checked through the supply chain. So yeah, that would be, but unfortunately you don't have stewardship schemes for everything, I think. So yeah, so just be aware of what you're buying and think about whether it might be legal or illegal, and don't bring it home if you don't buy things abroad and bring them home.
Thank you very much, Lucy. And I'm afraid the time has run away with us. It's just been wonderful. Thank you all for being here tonight and listening to it. Thanks to our panel. Thanks to Lucy, to Fabio, to Lawrence, and to Ryan for giving us the wealth of information and knowledge that they have. And I think you can all agree that the power of the science to determine the traceability and origin of where things come from is so important to protect people, animals, places that we live in, and the planet that we want to leave to our next generations. So if we just take our hands to thank everyone for their